Hi, and welcome to Module 8, the last module in Lecture 6. In the previous 7 modules, we introduced the concept of extrema, discussed how to find them. Now we're going to look at particular examples of using extrema for the benefits of some substantive aspect of political science. These are also general examples that apply to social sciences in general, so they're not just political science only, but they're tailored mostly for political science. Okay, so the first example we're going to look at is the example of game theory. In particular, this is actually only decision theory, but good enough for now. So, let's consider a situation in which you have some person, say you, and you want to contribute to some campaign because you think you're going to get something out of it. Right? It could be some expressive benefit of contribution, makes you feel good about yourself, or it could be some actual favor you expect to get from the politician should that person be elected. Okay, so there's something you're going to get from this. Let's start off by assuming something you get is 2x, where x is your contribution. Let's assume also that you actually have some other use for your money, right? Had you the money you would have given had you the money that you end up giving to the politician, you could have instead done other more fun stuff. So let's say the cost of losing that money is 1/2 x squared. This then would be the utility function. Now the entire point, well not the entire point, a lot of the point of decision theory is to identify the action that is best for you. In this case, it's the action that maximizes your utility. How do we do that? Well, we just went through an entire lecture on how to maximize a function. So let's do the same steps here. First, we'll calculate the first derivative. Well, that's 2 minus x. Right? All we did is use the power rules and the fact that the derivative was linear. Now we're going to set that equal to 0. Which implies that x star is 2. Great. So that gives us a local extrema possible. Now we use the second order condition. The second order condition tells us this. The second derivative is -1. That is less than 0. So that implies we have a local maximum. Note that this is true for all possible x, so this thing is globally concave. We don't have to worry about the exact value of x star, but still x star equals 2 is a local maximum. Now if we had no other information about bounds of this thing, we would just say, okay, x star equals 2 is the maximum. We do have information though. We could say you can give between 0 and let's say 5. Let's check those bounds too. The utility at 2 is 4 minus 2 equals 2. The utility at 0 equals 0. And the utility at 5 equals 10 minus 25 halves equals -2.5. Clearly, 2 is the biggest of those, so 2 is not only the local maximum, it's the global maximum. And in general, you often find if the function is globally concave, then it's easier to find. Then it's easier to transition from local maximum to global maximum. You're going to find the true maximum at the local maximum of a globally concave function. So that's that. That's the first example of this. And that doesn't matter if we can change the bounds all we want. Whatever bounds we pick, they're going to have a lower value than 2. What about if we change the utility function a little bit? Let's now swap this out for that function. So instead of 2x, it's 2 times the square root of x. What does that mean? Well, it means that you actually get less relative benefit for your contribution. And in particular, the more contribution you give, the lower the marginal gain of additional contribution dollars. Let's do the same thing and analyze this one. Okay, again. Now, the square root of x is x to the 1/2. So you pull down a half and subtract 1 from the exponent. That gives you the 2's cancel. The 2 and the 1/2 cancels. So you get 1 over the square root of x. That's x to the -1/2, which is 1/2 minus 1. This thing remains x. Next step, set it equal to 0. Well, what does that get you? See, that implies that 1 over the square root of x star equals x star, or x star square root of x star equals 0. Well, that's pretty straight. Oh, sorry, equals 1. So what works there? Well, if you put in 1 for both of these things, you get 1. So it looks like it's 1. So here's the new maximum. It's now 1. The maximum has decreased. I shouldn't say maximum. The extremum, the stationary point, has decreased now, because of this benefit for contribution. Let's now check out the second derivative at that point. Well, now, first is the derivative of x to the negative 1/2, which is negative 1/2 x to the negative 3/2, it's x star, minus 1. If x star equals 1, then this thing is 1, and that's going to equal negative 3/2 is less than 0. So again, we have a local maximum. We can check again to see if we're getting anywhere. Well, you plug in 1 to your function, you get 2 minus 1/2 equals 3/2. At 0, you get 0. At 5, you get 2 square root of 5 minus 25 over 2. That's even lower than before. That's still negative. So again, we have the local maximum being a global maximum. We keep this up and continually decrease the value of our contributions, and eventually we would find that the local maximum is no longer different from the bounds. One way to do this is to change the utility function to provide less marginal benefit for contributions. For instance, if I stuck a 10 in here, then each additional gain in x would be worth less than it was before, because now you're further up the square root curve for utility. If you actually solve this, you would find that the maximum would be very close to 0. If you made 10 100 instead, you wouldn't find any maximum at all. There's a better example of this kind of process in the book using logarithms. We, however, are not going to talk any more about that, and instead go on to a second example involving statistics. Now, let's posit first a linear relationship between two things. Let's say that something y, let's say voter turnout, is related to something x, let's say education. And let's say that they have some relationship that's determined by beta, so that a 1 unit increase in education led to a beta unit increase in y. This is a simple linear model because it posits a linear relationship between x and y. If it were x squared or x cubed or whatever, it would not be linear. But this is the kind of model you see a lot of in the social sciences. Now, we don't think things are deterministic, so we need some stuff, some error we're not sure about, some stuff that we're not sure about. We're going to include that as epsilon. Epsilon here is an error term. It's all the stuff that we believe might go into turnout that's not taken into account by education, and we hope that it's not correlated with education. And this is the standard linear model that we examine often in the social sciences. Now, what do we do with this? What do we want out of this? What we want is to find the beta, the best beta here, the beta that most explains our dependent variable. How do we do that? We do that by finding the beta that minimizes error. In particular, we want to find the beta that minimizes squared error. Right? The beta that minimizes squared error is the beta that provides the best fit for our relationship. So, what's that? Well, we can move this around and get that epsilon squared is equal to y minus beta x squared. Let's call this a function of beta. This thing is going to be what we're trying to minimize. How do we do that? Well, what we do is we minimize it using the same technique we've been using so far in this lecture. Now, a quick aside, this only works if y and x are single numbers. In general, y and x will be vectors, which you'll deal with when we get to, and we'll talk more about that when we get to vectors in part 4 of the class. In this case, just assume that y and x are a single data point each. You can't obviously do this with a single data point each in general, but you can certainly minimize this function with a single data point. And it turns out that the techniques we're using here as far as calculus goes will be very similar to what we would use with vectors and more than one data point, but we'll stick to one for now because we don't have vectors yet. Okay, so here's our function. We're trying to minimize it. And y and x are just numbers. They're no different than 2 or 3, so we can ignore them. All that matters is beta. We're trying to minimize this function with respect to beta. How do we do that? Well, first we find the derivative of the function. Now to do that here, we're going to have to use the chain rule. Where we have a function composition. We have this is actually equal to g of h of beta, where g of beta is beta squared, and h of beta is y minus beta x. How do we use the chain rule? Well, we'll call this thing u. We'll say that g prime of u equals 2u. We'll say that h prime of beta equals negative x, because the y is just a constant, it goes away. And so is the x, it sticks around, but it's just a constant. Now we're going to substitute in back again for g of h of beta, which will equal 2 y minus beta x. And then finally we multiply it by h prime of beta to give us the value. Sorry, this should be regular. That's just f of beta. F prime of beta will be 2 y minus beta x times negative x. There we go. That's f prime of beta. What do we do with this? Well, now we have to set it equal to 0 to find the optimum, or rather a possible extremum, the stationary point. Well, we can multiply it out and we get negative 2yx plus 2 beta x squared equals 0. The 2's cancel. We can put the yx on the other side, divide by x squared, and we get that beta equals x y over x squared. That's beta star. These are all beta stars. Okay. And that is the optimum beta. Sorry, I haven't gotten there yet. That's the stationary point. That's the only stationary point here. There are no bounds listed, so this is the only stationary point. Sorry, this is the only stationary point. Now we have to compute the second derivative. The second derivative, which I'll put over here, sorry about the lack of room here. The second derivative, remember y and x are constants, so that first term vanishes. The second term is 2 beta x squared. The derivative with respect to beta of that is going to be 2x squared. That's always positive, regardless of what x is. Therefore, we have a local minimum, which is good because we wanted to minimize error, so minimizing our function is what we want. There's no bounds listed, so this is also the global minimum. And we have calculated the global minimum. This beta star here, xy over x squared, is the value of beta that minimizes the squared error, and is therefore the value of beta that gives us the best fit to relationship between y and x here, between turnout and education. Now, at this point, you may be wondering why we're doing this, right? Well, A, this is a real example of a real linear model that you can deal with. But B, this is actually not far from what you'll get when you have more than one data point. When you have more than one data point, the actual value of beta looks like this. X transpose X, inverse, X transpose Y, ignoring for the moment all the transposes. You see that you have basically x squared, inverse is 1 over x squared, and xy. So xy over x squared. There's not much difference from what we just did, and beta using more than one variable and more than one data point. The calculus is very similar, has the same character, and you get it by using the exact same kind of techniques we just finished learning. And that's it. So now, after this lecture, and this finishes not only lecture 6, but also part 2 of the class on calculus, you've now started off learning what the derivative was, and in only a few lectures, you can now start it in computing derivatives that are reasonably complicated, integrals that are reasonably complicated, and and more importantly, have a grasp of what the derivative and the integral means and how it's used in various contexts. In particular, you now know how to optimize a function, computing either the minimum or the maximum of a function, which, as we saw, helps in both statistics and game theory, and you'll be using in a variety of ways throughout your education and future career. So that's it for part 2. You have a choice now what to do next. You can go straight into part 3, which is on probability, or if you want to skip ahead to part 4 on linear algebra, you now have you actually could have done that earlier before calculus, but you have all the necessary tools for that as well. Thank you very much for watching.